Okay, so guys, this is our connecting point. Again, you've got three things in front of you. You've got your equation sheets, you've got your book open to 663, and you've got your notes that you started last time. So let me just tell you up front, guys, today's going to be a relatively short day. Given how the day started when it was much like unto romper room, let me just tell you right now, you are going to have time to work on your homework. So guess what we're going to do? We're going to work on homework. Okay, so guys, with that sort of laid out up front, guys, let me help you re-engage with the conversation that got cut short last time. So last time what we did is we laid out this interesting idea that water has the mystical, magical ability, because it's amphoteric, to actually react with itself. And when water reacts with itself, one water molecule steals a proton from another water molecule, one being an acid, one being a base. And when that happens, we end up with hydronium ion formed. That makes it an acid. We end up with hydroxide ion being formed. That made it a base. And then guys, what did we decide about these two concentrations in pure water? They're the same, because every hydronium that forms also forms a hydroxide. Those are equal in concentration. We found out that Kw truly is a constant with a value at 25 Celsius of 1 times 10 to the negative 14th. We did the math and we figured out that each of these then has a concentration of 1 times 10 to the negative 7th. And we had that magic moment where we realized that that was pH 7 and everything in our world made sense. Remember that? Okay. So then, guys, we had this conversation and we talked about the idea that we can treat this thing like a seesaw. Oh boy. No. And you know what, guys? I'm going to have to calibrate this really quick because I've got to be able to write. And I did that this morning and now it doesn't seem to care. Just 1 second. Oh no, not that. It's off the screen. I don't even know where that dot is. And, oh! Wait a minute. No, I can't do that. This is like a fitting analogy for my life. Let me see if I can just quit this. Okay. Yeah, it's funny. I got all of the new equipment for my new system. It's all up there. And I emailed the guy and said, hey, let's install it. And he emailed me back and said, you don't have all the parts. And I said, what am I missing? And he said, the brackets. And I said, no, they're in a box. And he said, you still don't have all the parts. And I wrote him back this morning and said, either you come install it or I'm going to do it myself. And he didn't write me back. So, yeah, this is ridiculous. Come on. It's funny because Alpine School District still treats technology as if it's a luxury and not mission critical for education. Your computer doesn't work? Be a professional. Figure out a way around it. This is all being recorded. Okay, so guys, here's the idea. We said that because Kw is unchanging, that means that we have this fixed point. And this fixed point becomes that point, if you will, between the product of the concentration of the hydronium and the hydroxide, which then tells us if this goes up, that's got to go down proportionally, and vice versa. You comfortable with that idea? Okay, so then the question becomes this. How do we know this concentration in the first place? And the answer is pH. Okay, so that then allows us to have a little review conversation of pH. And guys, this is where you may want to start taking notes. Again, we did scratch this briefly on the board. The thing that I didn't do is do this. But we've got to, again, guys, make sure that we're comfortable with this idea that these two expressions are equivalent. Why are they equivalent? Because hydrogen ion and hydronium ion, because we are intelligent chemistry students, are the same to us. So guys, you'd better be able to make sense in your head, and I'll give you a minute to do it. Why are those the same? And I don't need you to say it. I want you to make sense in your head, and then we'll talk about it. Because what is it that's true that makes these the same? Here's the surprising answer. This doesn't exist. Right? You guys comfortable with that idea? Guys, the reason that these are the same is because we understand that these are descriptive of acids. What do acids do in water? Give away protons. Where do the protons go? To the water to make what? To make hydronium. So guys, the reason that these are the same is because this doesn't really exist. There is none of this in an acid because all of this has hooked up with water to make this. And because we all understand that, we can then say that we don't necessarily have to include the water because we all understand collectively that that's really what's going on. Get the idea? And then it just simplifies the picture. Okay, so in review, here you go. Guys, these are the things that you need to remember right now about pH. First of all, pH is a mathematical expression of the acid-base concentration or strength of an acidic or basic solution. Remember that low pHs are acidic and that higher pHs are basic, with the center point being 7. And guys, what pH does then is it allows us a mathematical insight into the concentrations of water-based acidic and basic solutions. So guys, let me let you catch up. We'll entertain questions if necessary. It's probably worth mentioning, obviously, that pH is a logarithmic scale. I trust that you're mathematically attuned enough to understand that that means that it's changing by powers of 10, but we also understand that this is a negative exponent, so the larger that the pH gets, the smaller the concentration gets by powers of 10, because these are decimals smaller than 1. So a pH of 1 is 10th molar, a pH of 2 is 100th molar, a pH of 3 is 1000th molar, and so on, because these are negative exponents, so you're raising the power of 10 to a negative exponent. Does that make sense? Do you guys remember that? Ask if you don't. You okay with the ideas? And are you caught up? Is there anything here you want to talk about or continue to write? You're okay? Okay. So guys, now we need to get into some new territory. And the idea is this, and we didn't talk about this last year. We didn't talk at all last year about bases other than to say they're the opposite of acids. Guys, obviously in this class, we need to touch on bases as well as acids. So the idea is that right now you understand that pH lower than 7 is an acid and a pH higher than 7 is a base. But guys, we've got to extend our understanding. And so in order to do that, I would offer you, first of all, this, oh gosh, will it not let me do it? Come on. Come on. Why isn't it there? Hold on, maybe it'll pop in. There we go. Okay, so guys, understand that that relationship is described by the equation across the top of the screen. We now understand that as a solution increases in hydrogen ion concentration, hydronium, it decreases in hydroxide ion concentration. It's that seesaw effect. Well, guys, if you look down on page 663 in your book, you will find this table. Isn't it there? Guys, find the seesaw in the table. There's two seesaws. Because now, guys, we not only have pH, which is the negative log of hydrogen ion concentration, what's on the far right? pOH, which you could probably figure out, is the negative log of the hydroxide ion concentration. So guys, let's do this. Let's not start at pH 14 because there we've got a 0, and 0 sometimes are hard to think about. So why don't we start at this spot right here? I would encourage you not to write in your book, but let's have this conversation. Guys, down here we've got a very, very basic solution. So in a very basic solution, what are we going to have more of? Hydroxide or hydronium? Hydroxide, of course, right? Because it's a base. So guys, look at the way this plays out. We are actually given 4 pieces of data relative to this one solution. First of all, notice that we're given pH. And that pH is very, very high, telling us what about the solution? It's very basic. But guys, this is the place this becomes counterintuitive, because you're thinking very basic, which means it's very concentrated. And it is. But what is it very concentrated in? Hydroxide. Guys, this is the thing that it's very concentrated in. It is 0.1 molar in hydroxide. But that ain't where the pH comes from. The pH, by definition, is the concentration of hydronium, of protons. And guys, you know this connection, right? The pH is the exponent of the negative exponent of the concentration of hydronium, or hydrogen. So this is 10 to the negative 13th molar in hydrogen ion. Can you picture 10 to the negative 13th? Guys, that is 0.003456789101112 molar. That is the concentration of hydrogen ion in this very basic solution. But what is the concentration of hydroxide ion? 0.1 molar. It is very concentrated in hydroxide, not very concentrated in hydronium, as you would expect, and that's where we get a high pH of 13, indicating a very small concentration. But now, guys, we introduce this idea of pOH. And check out the pOH. Does that make sense that it's 1? Do you see the connection? That is, if this is 10 to the negative first molar, then the negative log of the hydroxide ion concentration would be 1. See the connection there? And so then, guys, we know that substances that have very high pHs, which are basic, have very low pOHs, which is new to us, telling us again the concentration of hydroxide. Do you see the connections there? So guys, talk to me about the seesaws. Where are the seesaws in this relationship? Well, here's one of the seesaws, right? This is the one that we've talked about. We understand, and this is this seesaw, that as this goes up, this goes down, and vice versa. And actually, we looked at this one. So we said, as this goes up, I'm installing it without him. This is ridiculous. So guys, what we've said is that as one goes up, the other goes down. This seesaw is this seesaw. You good with that idea? But now we've got another interesting relationship. Do you see the pattern in the pHs and the pOHs? Go, Joey. As good. So we've got that seesaw, right? As pH goes down, pOH goes up. So maybe we should think about it this way. Why is this a seesaw? Because this is constant. But Joey found the other seesaw that says as this goes down, this goes up. But what is the constant here that makes that true? Do any of you see it? Exactly. pH plus pOH equals 14. Check it out. 13 and 1, 12 and 2, 11 and 3, 10 and 4, they will always add up to 14. Why? Because these exponents will always multiply out to 10 to the negative 14th. And if you understand the rules of logarithms, both of those things have got to be true. Whether you understand the math behind it or not, we now have two seesaws. And Everett, this is getting at what you were taking us to in question 35. We've just got to figure out how to make these seesaws play with each other. Okay, so guys, again, the idea is this. We now understand that pH plus POH is equal to 14, right? Find it on your equation sheet. Yeah. Oh yeah, absolutely. Yeah, I didn't even protect you from that last year. Yeah, absolutely. Yeah, you most definitely, because you can still run them through your calculator. Yeah, for sure. Yep. So guys, do you see pH plus POH is 14? Yeah. And you also still see the equation at the top. The Kw is hydrogen times hydroxide. So now we've got two of these seesaws that we can play with. So guys, just to make sure we're cementing these ideas, maybe go down here and let's take a look. Where's something pretty clear? Like Coke. Take a look at pH 3. So guys, looking at pH 3, as we would expect, the hydrogen ion concentration is 10 to the negative third, 0.001. That then means the hydroxide, or hydroxide ion concentration is 10 to the negative 11th, and then similarly, as we understand, that gives it a pOH of 11. You good? Get the idea? Yeah. Thank you. Carson, I don't know. So if I understand your question, you're saying, does this only work when we're talking about aqueous acids? Yes on this, right? Because, and this is the part that backing up. Why does all of this work? Why is it, guys, that as pH goes, as H goes, as hydronium, why is it that as hydronium goes up, hydroxide goes down? And the answer is, I think you're understanding, Carson, is that because this is all cast against the backdrop of water. And so water becomes our source of both hydronium and hydroxide. What we haven't done, and frankly this is purposeful because I've tried it and it's blown up in my face, is in years past, and it's been a while, I've tried to expose my students to the chemistry of why that's true. Why is it when we add an acid to water, do you want to try it? Let's see what happens. The worst thing that happens is you're so completely confused you want to go away. But think about it this way. So we've got, am I writing? Come on, right. We've got water plus water in equilibrium with, come on, baby. In equilibrium with hydronium and hydroxide, okay? And it is equilibrium, right? So what happens, you know what? I think we can do this. So the question, guys, the question that we're asking is this. Why the seesaw? And so the idea is this. Imagine that this is a bucket of pure water, right? And if we dump in an acid, what are we changing about this equilibrium? This is going up, right? So dump in an acid, what we're doing is adding a source of protons. The protons immediately increase the concentration of hydronium ion. As that happens, what effect will that have on hydroxide? It'll go down, right? Same side does the opposite. We can let it be same side does the opposite side does the same. But Le Chatelier's principle and all that we understand about equilibrium would tell us that this would go down proportionally. And then similarly, if this goes up, this goes down. So the reason they seesaw is because we're talking about an equilibrium that exists in water. Why did that go bad before? I don't even know. That wasn't that hard. But I've done this before with other classes and they've gone, and it's just been day over. So that's why. So then your question was, does all of this only work in water? And I've never thought about it, but I think the answer has to be yes. because the only reason this works is because adding acids and bases is doing the seesaw because it's tweaking the equilibrium of the autoionization of water. Go ahead, Josh. I don't know. I mean, we're just going to do water. And we're going to talk about it. We're going to talk about buffers. And when we talk about buffered systems, we will see that other systems have equilibria that we can tweak, but not as foundationally as with water. But yeah, we're going to do that with buffers. So I said I don't know, and that's not true. Yes. But here's the problem, though. We're going to create buffers in water, and so water will still be a component. Spencer. And you'll see that they do, and again, we're going to create buffers with them. So you guys, you okay with all the monkey business? Okay, so now let's see what happens. Come on board. Okay, what's it going to do? I don't know. Okay, so guys, let's try this together. I think if we can answer this, I think question 35 in the homework is going to be well within play. So guys, the question is this. If we have a solution that has a hydroxide ion concentration of this, what is its pH? But guys, and the answer is not 11. It will be near 11, but why is it not 11? It's not a 1. But guys, here's what I want you to do. Please spend the time to write out an appropriate solution to this. I understand that you can plug and chug this through your calculator, but guys, understand that the reason I'm asking you this question is I need for you to have the experience of solving this problem and realizing that maybe nobody else in the room did it the way you did. But you're only going to have that experience if you do it. Do you have my calculator? Negative. You know what? I think it's over there somewhere. Huh. Yeah. Oh, wait. No. There it is. Thank you. So guys, I get 11.3. Here's the trick, and I know better than to try to write this down for you because I've given up on this board as much as I can. So guys, I would propose to you that if we were to trade papers or put up examples, this is kind of interesting. With this new system that I've got, there's actually a Wi-Fi hotspot built into the projector, and it shares out, actually it's got a little web server in it, and it shares out an IP address, and you can get out your phone, connect to my projector with your phone, and then it turns your phone into a writing tablet, and you can actually write on your tablet, and I can project it on the wall. If it works. Yeah, but if you had an iPad, it would be great. Okay, but anyway, all that to say, guys, some of you did this. Some of you, in order to solve this problem, because of the screen that we looked at previously, some of you said, okay, I've got the hydrogen ion. All right, I'm going to write. Some of you said, okay, I've got the hydroxide ion concentration, and you did this. You said, come on, baby, Kw is hydrogen times hydroxide, plugged in that sulfur hydrogen, and then you went pH is the negative log of hydrogen. But guys, some of you realize there's another way to do this. And you went like this. You said pH is POH is the negative log of hydroxide, and then you said pH plus POH is equal to 14. Which one's right? Both of them. Now guys, here's the thing that you've got to understand. This is a simple example, and you get into the middle of this and you're like, I picked one or the other and neither one's right, and yay go me, I got to the end. But guys, the problem is that when these get a little more complicated, you've got to remember that you have all of these tools available to you in your toolbox. So relative to, as Everett got us thinking about something like number 35, remember that these equations are available to you. So guys, regardless of how you handled that, then that brings us finally to this interesting idea of POH. That in the same way that we can take the negative log of hydrogen ion and get pH, we can take the negative log of hydroxide ion and get POH. So find that equation on your equation sheet. And then along the way, we combine these two thoughts together, first in the table on 663, but now mathematically as we found on our equation sheet, and also realize now, guys, we have this equation, pH plus POH is equal to 14. So now, guys, we've got 4 equations that we can manipulate, right? pH is the negative log of hydrogen, POH is the negative log of OH, pH plus POH is 14, and then KW is hydrogen times hydroxide. And guys, by leveraging those 4 equations in lots of unique ways, we can make a pantload of conversions to get where we need to be regardless of the information that they give us. So there you have it. So guys, what questions do you have about all of the interplay between hydrogen and hydroxide and pH and POH and all of that lovely stuff? You guys okay? Okay, so let's round out today's conversation then by talking about strong acids and bases. So, guys, let's remind ourselves of a couple things. How many strong acids are there? 7. Refamiliarize yourself if you don't remember which ones they are. How many strong bases are there? You now feel violated. So, guys, let's get you over the violation. You now understand that it's not just the group 1 and heavy group 2 hydroxides. They used to have a table of these. That's interesting. They took it away. Oh, there it is. Turn to 657. So guys, understand that this is not an exhaustive list. But with that said, looking on 657, allow your eye to fall at the top left of the page. There's our strong acids. Well, 3 of the 7, right? Hydrochloric, sulfuric, and nitric. Then guys, notice over on the right, you've got their conjugate bases. And notice there's that word that we use, negligible. So these are our worthless conjugate bases. But now, guys, we're going to have a significant thought. You ready? What is it that makes a strong base a strong base? And we said that it means strong acid is strong acid. We've said what makes a strong acid, and we've said the answer is a negligible conjugate base. But guys, again, these are comparative terms. So relative to what is something strong? And relative to what is something negligible? Do you now see the answer? It's actually in a light brown box. Water. So guys, what is it that makes something a strong acid? And the answer is, it's better at giving away hydrogen ions than hydronium ion. Do you see that? Look at the top 4 species in the left-hand column. HCl, H2SO4, and HNO3 are all strong acids because they're better at giving away hydrogen than hydronium. So how does that work? Well, guys, it's not negating the thing that we said earlier about a strong acid being a strong acid because it has a worthless base. Go to the other side of the table. How does this work? Well, guys, the connecting logic is this. Chloride, HSO4 minus, and nitrate are negligible, right? But negligible compared to what? Water. See, guys, what this means is these 3 substances can't steal hydrogen from water. And those are the connecting concepts. Do you get the idea? Guys, for some of you, this is confusing, but for some of you, this is magical. Because, guys, water, the most plentiful substance on earth, you now understand because so much of life is acid-base chemistry, right? Yeah. Well, guys, it turns out that the most plentiful substance on earth and the very thing that we need in order to sustain life is not only just an acid and a base perfectly, but also is the very basis of the definition for what is an acid and a base. Because a strong acid is just better than hydronium, and a strong base is just better than hydroxide. Guys, this to me is mind-blowing. But deal with it as you will. But guys, that's the connecting point. You get the idea? You okay? Okay. So with all of that said then, guys, let's remind ourselves, what is a strong acid? What is a strong base? Well, guys, what does the word strong mean in our vocabulary? Goes to completion. And because this is true, guys, this is true. This you want to write down. Because this is not always true. It is for strong electrolytes, but not weak ones. And the thing is this, guys, when we talk about strong acids, we consider the concentration of the acid to equal the concentration of hydronium ion. And guys, what I want to do is I want to show you a negative example of that and a positive example of that. So that you understand what we're saying. So here's what we're going to do. Let's consider a 1 molar solution of HCl. And let's consider a 1 molar solution of acetic acid. Okay, so if we picture a beaker with 1 molar HCl in it, what's in that beaker? Remember, guys, you're going to be asked to answer questions like this on the test. So we've got hydronium ion. We've got chloride ion, we've got water, right? Now wait a second. I thought we said that this is a 1 molar solution of HCl, and we don't have any HCl. Where'd it go? Into the water. It reacted with the water and formed hydronium, and it formed chloride. So guys, there is none of this in a 1 molar solution of HCl. But from this, we can calculate the concentrations of the other. So what is the concentration of hydronium? 1 molar. What's the concentration of chloride? 1 molar. Why is that true? Because all of the HCl that we added went to form hydronium and chloride. Get the idea? Okay. So guys, what about this? I'm going to make a bigger beaker because the names of these are going to be bigger. Guys, what if we've got a 1 molar solution of acetic acid? What's in that solution? So we've got acetic acid. Why do we have acetic acid where we didn't have hydrochloric acid? Because it's weak and it reaches equilibrium. And actually, guys, you're going to find out there's a ton of this. I think it's like 97.8%. We'll calculate it next time. What else do we have in there? High acetate ion. Come on, baby. Come on. Just this and this. And that's it. Guys, and water. And water. But guys, that's what we've got in solution. But now here's the trick. What are the concentrations of the acetate and the hydronium? Well, they're the same, but are they 1 molar? No. Will they be greater or less than 1 molar? Less than 1 molar, because a lot of this doesn't even break apart. On Friday, we'll figure out what the concentration actually is using an ice box. But guys, these are not 1 molar. So the idea behind this statement is this works for strong acids. The concentration of the acid is the concentration of hydronium. This does not work for weak acids because by definition it doesn't completely dissociate. You get the idea? Okay. And then guys, the bottom line then is this also works for bases. If you've got a strong base, the concentration of the base is the concentration of hydroxide ion. You good to go? We're done. You're okay? Okay. So guys, revisiting this then. Come on, baby. There's your homework again if you need. And guys, as advertised, you have about 30 minutes. Yep, yep, finish it up. So guys, I would love to help if you want to talk questions. If you saw things that you didn't understand as you did the homework last night, revisit them because I think you'll find them more accessible now. And